OpenAI and Anthropic clash over compute advantage. Big tech puts financial heft behind next-gen nuclear power. The push for highly efficient open-weight models. If you're trying to navigate the massive shifts happening at the bleeding edge of technology, you already know the landscape changes daily. Welcome to AINUCU.com, AI news you can use, your daily dose of AI know-how. Let's get straight to the reality check. The future of human intelligence isn't going to be decided by who has the absolute smartest whiteboard equations. It is being decided right now by who is hoarding the most digital, raw horsepower on the planet. The algorithmic elegance of yesterday is being completely steamrolled by the sheer physical infrastructure of today. And we are looking directly at the mechanics driving this industry, stripping away the PR and explaining the actual structural physics of the tech landscape, because you really need to know what's happening beneath the surface. We are looking at a massive structural clash at the very top of the food chain today. OpenAI is actively and very pointedly telling its investors in a private memo that it has secured a definitive, crushing computing advantage over its main rival, Anthropic. They aren't just hinting at it. They are communicating this superiority behind closed doors as a done deal, a permanent moat. They are reporting 1.9 gigawatts of capacity compared to Anthropic's estimated 1.4 gigawatts. This term, compute advantage, is doing an enormous amount of heavy lifting here. It is not some subtle boast about having a few extra servers in a rack somewhere. It is a declaration of supremacy in the only metric that currently dictates the pace, the scale, and the timeline of the entire artificial intelligence ecosystem. So, let's unpack the actual physics of that term, because if you are a developer, a strategist, or just an enthusiast watching this space, understanding compute at this specific level is mandatory. We aren't talking about enterprise server racks or high-end commercial cloud instances. We need to talk about what it actually means to string together 100,000 next-generation GPUs into a single unified cluster. When you move from a cluster of, say, 10,000 chips to 100,000 chips, the computer science fundamentally changes. It breaks all the old rules. You are no longer just dealing with raw processing power. You are suddenly dealing with the hard physical limits of networking latency and, honestly, thermodynamics. To train a frontier model, you are adjusting billions or even trillions of parameters across a neural network, and that requires synchronous parallel processing. The basic concept of gradient descent works like this. The model processes a massive batch of data, makes a prediction, calculates its error, and then updates the weights of its parameters to be slightly more accurate the next time. But when that model is distributed across 100,000 individual chips, every single chip needs to communicate its updates to every other chip almost instantaneously before the next batch of data can even be touched. If one rack of GPUs is just sitting there waiting on data from another rack on the completely opposite side of the facility, the whole thing stalls. The entire multi-billion-dollar system sits completely idle. The latency between node A and node Z cannot exceed microseconds, which is why you can't just rent spare compute from across the globe and stitch it together over the public internet. The physics just won't allow it. You need bespoke networking topologies like massive InfiniBand or NVLink switch fabrics, using thousands of miles of specialized optical fiber just to connect the processors within a single massive building. And those optical transceivers alone cost more than most startups raise in an entire seed round. That leads directly to the physical footprint. A compute advantage at this crazy scale is heavily dictated by real estate and utility grids. The silicon itself is literally just step one. When you are running a cluster of this magnitude, you're pulling hundreds of megawatts of continuous uninterrupted power. You are essentially negotiating with regional utility companies for the equivalent power draw of a medium-sized city just for one building. And all that electricity flowing through the silicon generates an astronomical amount of heat, bringing us directly to thermodynamics. We have officially crossed the threshold where traditional air cooling in data centers is physically incapable of preventing the chips from literally melting. You have to design direct-to-chip liquid cooling infrastructure, which is incredibly heavy. You have to re-engineer the structural integrity of the data center floors just to support the raw physical weight of the coolant piping and the water inside them. This completely highlights the flaw in the common assumption that anyone with enough cash can just buy a supercomputer. If a rival tech giant decides they want to match OpenAI's claimed 1.9 gigawatt cluster tomorrow, they can't just swipe a corporate credit card. There is no add to cart button for a gigawatt power substation. The supply chain reality is beyond brutal. The fabrication plants capable of printing silicon at this level of precision have years-long waiting lists. The packaging plants and companies manufacturing the high bandwidth memory that sits on top of those GPUs are completely tapped out. Utility grids take years to provision the necessary power drops, and getting the permitting for massive cooling towers requires immense local and geopolitical maneuvering. So when OpenAI claims a compute advantage, they are claiming to have conquered that entire physical and logistical supply chain. They're claiming to have locked up the fabrication queue, the real estate, the power contracts, and the cooling infrastructure years before anyone else can physically break ground on a matching facility. And this brings us to the mathematical law of the universe that makes this physical hoarding so incredibly valuable, the scaling laws. Over the last few years, empirical evidence has proven a very stubborn fact. Throwing more brute force compute at a model during its pre-training phase reliably and predictably makes it smarter every single time. Think of it like managing a massive global logistics network. Imagine two competing shipping empires. On one hand, you might have an incredibly brilliant, mathematically perfect routing software, the smartest supply chain algorithm ever conceived. On the other hand, your competitor physically owns a fleet of 10,000 massive cargo ships, and you only have a fleet of 5 local delivery vans. They win easily. They are going to move an exponentially larger amount of freight just through sheer, unadulterated brute force because they can cover every route simultaneously. In language modeling, the freight is the high-dimensional relationship between human concepts, logic, syntax, and facts. A low-compute model has to compress all those complex relationships, which means it loses the nuance. It hallucinates because its internal map of reality is super low resolution. But a high-compute model, backed by that massive fleet of cargo ships, has the vast parameter space and raw processing power to map those relationships with extreme fidelity. It doesn't just memorize text, it internalizes the underlying logic of the data because it has the raw capacity to hold all those intricate connections at the exact same time. Now, it's fair to push back on this premise. We are treating brute force compute as an insurmountable advantage. But what about algorithmic efficiency? We are seeing highly dense, relatively small parameter open weight models dropping right now that heavily outperform massive older models. They use a fraction of the compute, but they punch way above their weight class due to better data curation and clever architectural tweaks. So doesn't that prove a massive compute advantage can be neutralized? Well, it proves algorithmic efficiency matters immensely at inference time, when you are actually running the final model for the user. But it actually reinforces the importance of the compute advantage during the training phase. Those smaller, highly efficient models didn't magically bypass the need for compute. They utilized heavily optimized training runs and often trained well past the traditional compute optimal frontier. To make a small model incredibly smart, you have to hit it with high-quality data over and over again and run massive hyperparameter tuning to find the absolute perfect architecture. That trial and error requires enormous amounts of compute. If you have a massive compute advantage, you can spin up 20 different variations of an architecture all at the same time, test them all, find the single most efficient one, and discard the rest. Your rival, with less compute, has to serialize all those tests. They have to wait a month to see if one single idea worked before they can even try the next one. So compute literally buys you time. And in this industry, time is the only truly renewable resource. This perfectly transitions to the specific strategy behind this private investor memo. OpenAI isn't taking out full-page ads to announce this compute superiority. They are deliberately back-channeling this narrative directly to the mega-cap venture firms and sovereign wealth funds. The AI race has evolved into the most capital-intensive technological sprint in human history. We are talking about tens of billions of dollars in capital expenditure just to buy a seat at the table. A massive GPU cluster costs billions to build, but the silicon itself becomes virtually obsolete in roughly 3 to 4 years when the next generation of chips drops. To justify that massive initial capital expenditure, the resulting model has to generate historic, unprecedented revenue almost immediately before the hardware depreciates into a paperweight. Investors at this scale are profoundly risk-averse. They don't want to fund the runner-up. They are looking to back the monopoly. Here is where the game theory of the whisper campaign becomes utterly brilliant. If you successfully convince the heavy-hitting investors that you hold a definitive, unassailable compute advantage, you completely alter the investment landscape. The investors run the math, understand the scaling laws and supply chain bottlenecks, and conclude that compute equals dominance. They view you as the safest, most inevitable bet. So they consolidate their capital behind you, pouring billions right into your war chest. You immediately deploy it to sign more megawatt power contracts, scale toward that 30 gigawatts by 2030, buy more cooling infrastructure, and secure more fabrication pipeline. Capital secures compute, compute guarantees performance, and performance secures even more capital. Conversely, this starves the competition. If investors believe Anthropic is permanently structurally disadvantaged, they are going to hesitate to write the required checks. In this specific tier of development, if you lose the narrative war, you lose the funding war. And if you lose the funding war, your brilliant architecture is dead in the water. So, why is Anthropic the specific foil here? Anthropic represents the only other player right now demonstrating the talent density and track record to build true frontier-level foundational models from scratch. But more importantly, they represent a fundamentally different architectural philosophy, staking their reputation on safety, steerability, and interpretability. They heavily prioritize understanding the internal workings of the neural network. This intense focus on interpretability is essentially a massive compute tax. Imagine two companies racing to build the world's tallest skyscraper. The brute force compute advantage is like hiring thousands of workers to pour millions of tons of concrete and steel nonstop, building vertically as fast as physically possible. Anthropic's approach is like pausing every 3 floors to bring in specialized engineering teams to X-ray every single load-bearing pillar. They use tools like sparse autoencoders to map the internal features of their model, running complex structural diagnostics to guarantee the building won't ever sway or collapse. It ensures there are no hidden flaws, but it diverts resources. If you spend 30% of your available crew X-raying pillars, you pull labor away from pouring the concrete for the next floor. You have an inherent handicap in the pure vertical race. OpenAI is basically telling investors, Anthropic is spending all their cycles trying to microscopically understand the concrete. We are just building a bigger tower. The true race is happening in the shadows, measured by internal metrics we never see. But the implications dictate the timeline for the entire global economy. The threshold we are approaching involves autonomous long-horizon agents, models capable of conducting original multi-step scientific research or deploying complex software architectures completely independently. If a massive compute advantage releases a model that fundamentally commoditizes junior-level software engineering, every startup, enterprise, and sovereign nation has to instantly adapt. You are forced to build your products in a world shaped entirely by whoever hoarded the most hardware, creating an oligopoly dictated by physical infrastructure rather than pure software innovation. But there is a critical structural wall the entire industry is barreling toward right now: the energy wall. We assume hoarding raw power is the permanent trump card, but what happens when we hit the absolute thermodynamic limits of the global energy grid? Data center power demands are extending the lifespans of coal plants right now, straining regional grids to the absolute breaking point. Big tech is putting financial heft behind next-gen nuclear power, but regulatory and construction timelines for nuclear infrastructure are measured in decades, not months. You can't hyperscale your way out of physics. When there literally isn't enough power generation on the continent to spin up the next massive cluster, the compute advantage hits a hard, immovable ceiling. And that is the exact moment the entire paradigm violently flips. Before we get into the final takeaways, just a reminder that you can find more insights and structural breakdowns like this at AINUCU.com. When brute force scaling reaches the limits of physics, extreme algorithmic elegance becomes the only viable path forward. The victor of the AI race long term might not be the one who hoarded the most raw power today. It might be the one who anticipates the energy wall and engineers an architecture that completely bypasses the need for it. We might see a shift toward neuromorphic computing, hardware that mimics the biological efficiency of the human brain. The human brain operates on roughly 20 watts of power, about the same as a dim light bulb, yet it heavily outperforms a massive gigawatt GPU cluster in causal reasoning. Or we might see a shift entirely to inference time compute, where the model uses specialized search algorithms to think and simulate solutions in real time. If a player uses their perceived compute disadvantage to force extreme innovation in their architecture today, they could theoretically bypass the infrastructure monopoly entirely tomorrow. Necessity forces efficiency. And that is your daily dose of AI know-how from AINUCU.com, AI news you can use. The biggest takeaway today is that the ultimate battle isn't just about who controls the most chips right now. It is about who survives the transition when the power grid inevitably maxes out. It is a massive, high-stakes game of resource management, and the board is shifting daily. Keep building, keep questioning the narratives, and pay very close attention to the physical infrastructure underneath the software. Keep pushing the boundaries, and we'll catch you on the next one.